Thank you so much for joining us today. My name is Steph Nelson. I am an application engineer at Siemens. Your presenter is Pete Schaldenbrand. Pete, would you like to introduce yourself?
Yeah, I'm Pete Schellenbrand, also a application engineer at Siemens, like Steph, and looking forward to doing the presentation today.
Pete's going to talk about some early detection methods for bearing defects, a pretty cool topic. All right, Pete, you ready to teach us about bearing defects?
I'm going to try, Steph, and I'll ask the audience and everybody else for their patience as I go through this. Bit of a hairy topic, a lot of different types of bearings in the world, and people are duly concerned about them failing. For example, if you're on a ship of some sort and the engine or one of the pumps breaks down because of the bearing failing, that's usually a bad thing. Your ship might have to be towed in or something like that. And bearings, they get a lot of wear and tear. They tend to be one of the first things that can fail in a rotating piece of machinery. So with this seminar, we're going to talk about some techniques. Like you said, the key word there is early detection of the failures. We want to find the failure before it actually occurs so that we don't actually get to the point where it does fail and stops our equipment from working. If you look at all these bearings, they have some common elements. There's a thing called the inner race, and that goes around the shaft that is rotating. Then you have these rolling elements, whether they're ball bearings or rollers or whatever they happen to be. And then there's an outer race that's attached to the piece of machinery that the shaft is spinning in. So inner race, outer race, and rolling elements. And as a bearing's operating, Steph, it might produce some vibration, right? And orders are a vibration that is proportional to the speed at which the equipment is operating. If you had a bearing like this, Steph, and you had to guess what orders the bearing might produce, what orders do you think it might create?
8.
Yeah, you would look at this and say, hey, there's 8 rolling elements, so maybe there's eighth order would be really strong. With gears and things, you can always count the number of teeth. With the combustion events, you can count the number of chambers. But guess what, Steph? 8,
It's not true.
it's not true. Yeah. Bearings end up being a little bit more complicated because there's this relative motion, if you will, between the inner and the outer race. And if you look at this animation here, this will give you an idea. Do you see there's 2 red dots, one on the inner race and one on one of the ball bearings? See
Yeah.
that? Okay, well, they're going to line up here. And in the time where this shaft goes around once, we'll count the number of times, for example, that this bearing, you see that red dot? The number of times it hits the inner race will count up because
Okay.
you can actually have a different frequency as the bearing passes over the inner race and the outer race. All right, they're about to line up. 1, 2, 3. It hit about 3 times when that inner shaft went around one rotation. Did you see that?
It did.
Or yeah, and that has nothing to do with 8. Would you agree with that?
No, it does not.
And same thing if you were to look at the number of times it touches the inner race, etc. So bearings produce, actually, depending on their geometry. So here's a bearing that we'll use throughout our seminar here. We have a known fault on it. They produce some distinct and different orders. Talk about those on the next slide, but you can see that they're actually fractional orders. They're not, in this case, it's a 9 ball bearing. None of these are easily relatable to ninth order. Would you agree with that?
Yeah.
Yeah. So what these abbreviations stand for, I got on the next slide here. And you can see that we have the ball pass on the outer race here. And there's a formula where you can take the geometry of the bearing and you plug these dimensions into the formula and you'll get what they call the outer race frequency. The inner race, as the ball passes over the inner race of the bearing, this is the formula. And then you got the ball spin frequency. And then some of these bearings, they have like a cage that holds the bearings in place that rotates around. And this is the fundamental train frequency of the cage that holds the bearing elements in place. It's got this little dotted line here to indicate what we're calling a cage there. So you can see these equations are complicated and they have things like the contact angle and everything else. If you normally get a bearing from a bearing manufacturer, they often will give you these fault frequencies so that you know what frequencies to expect from the bearing. Have you heard of these fault frequencies before, Steph?
Yes, I have.
Like I said, we'll be doing an example here with this particular bearing, and we purposely induced a failure on it. So we measured it with and without a failure. We measured the vibration at the same location on the non-rotating part of the bearing with the fault present and without the fault present. And we purposely made a fault on the outer race of the bearing. The data we'll analyze is around 2000 RPM, and so we would expect the fault around 121 hertz, 120 hertz or so. Does that make sense so far?
Yep.
All right. I'm not sure what's next here. Oh, it says let's try it. So we're going to do a little demo here where we'll analyze the data with and without faults on this bearing and see what happens. So I have TestLab Neo here, and I got this bearing data here, and I got the data with a fault and without a fault. Looking at the time data here, Steph, can you tell which one's the bad one and which one's the good one?
Not just based on the visuals, no.
Yeah, sometimes the green one has spikes that are higher than red and vice versa. Yet one of these has a fault in the outer race and one does not. So already it's a little bit not so obvious what's going on. But we know these fault frequencies, right? So I could take this time data, put it in the input basket, and then grab something like a spectrum average here, and then hit run, and we could look at the FFTs. And what was the frequency we're looking for again?
121 hertz?
Yeah, roughly. And so I got the spectrum of the vibration data here. And I guess which one's good here? It's the green one is good. It's good that we have green is good, red is bad. And it's on the outer race. So where would we expect to see a peak?
Around 121 hertz-ish?
Well, first of all, do you see a clear peak there?
No, I do not.
I don't see a clear peak there either. I see lots of other peaks. And in fact, this fault frequency of the bearing is pretty small. If I was to zoom in amplitude-wise, I'd say there's right around 120 or so there. There is hardly any difference between the bearing with a fault and without a fault at what's supposed to be the fault frequency of the outer race. Would you agree with that?
Yeah.
Yeah. Not only that, it's buried in there. It's hard to see this fault frequency. There's a lot of other things that are going on in this rotating system, and the vibration from the bearing can be pretty small. Now, I'm going to do something else here. I'm going to go to limits free, and we collected this data up to a very high frequency. And now if you were to look at the good bearing versus the bad bearing or the faulted bearing is red. Anything look different to you here?
The peaks around like the 1,000, 20,000, 30,000, or sorry, 10,000. They're all a little redder.
Yeah, they're all a little redder. But I'd say there's a pretty big difference, and it's kind of a weird frequency range around 32,000 to 35,000 hertz. Is that a fault frequency of this bearing?
No.
No, it's not. So kind of interesting that the faulted bearing shows a difference at a very high frequency, something perhaps that we weren't expecting. I'm going to go back to my PowerPoint here. And again, we didn't see much of a difference around 120 hertz. When we went out high in frequency, we could see quite a big difference in frequency. And there's a few reasons why a bearing that has a fault in it shows something that high. If you think about the outer race, you might have something like, you could call it a pit or some kind of imperfection that's developing on the outer race. And whenever the bearing passes by, it creates a impact event. Does that kind of make sense to you, Steph?
Yep.
Now the bearing isn't in complete failure mode. right? But over time, as the bearing keeps passing over this pit, it'll grow and grow and eventually make the bearing fail. What happens is you start getting these small impacts that are an early indicator of the fact that the bearing will fail. In this case, we're getting on this outer race. And so a bunch of small impacts, and an impact short in time duration, but in the frequency domain, what does that look like, Steph?
A bunch of frequencies.
Yeah, very broad in frequency. Yeah, and that is part of the reason we can see a difference there at the very high frequency range of 30,000 up to 35,000 hertz. And we don't see it anywhere else because these impacts are pretty small compared to the general vibration going on. Another reason, though, why we can see that difference is because the accelerometer that we might be using, a lot of these accelerometers have a resonant frequency. There's a mass in there that basically is on a spring, if you will. And at some frequency, you have a resonance inside your accelerometer where it really exaggerates the vibration. And in this case, the accelerometer we used has an internal resonance around 30 to 35,000. And so that's another reason these very faint impacts, it's able to pick them up and show a big difference because it's very sensitive in that frequency range. If you're used to using accelerometers, typically you want to measure in the flat range where it's not amplifying the vibration artificially. Kind of interesting when you're doing bearing analysis like this, it's actually beneficial to take advantage of the natural frequency of the accelerometer because it can exaggerate the vibration. And again, just a visual here. This isn't real per se. We have all this vibration going on in the rotating equipment, lots of gears and other types of vibration. But inside the data, buried within, if you will, are these small impacts that are occurring. And with that accelerometer resonance, and with the fact that these impacts are very broad in frequency, we can really only detect that early failure that's happening, creating these small impacts, shows up at this very high frequency. If you knew this, Steph, that there's this high frequency difference, what do you think we could do to process the data a little bit to visualize this failure a bit better?
We could filter it.
Yeah, so what kind of filter would you do?
To get the high frequency content?
Yeah, from like 30
filter?
to 35 to high pass, or we know that the resonance is over a certain range. We could do a band pass filter. High pass or band pass might work. But we know in this case, 32,000 to 35,000, if we apply a filter, band pass filter around that range, we might see a bigger difference. Here I'm giving it away, but let's actually do that here. How would we apply a filter here in TestLab Neo?
You'd have to add the filter method.
Yeah, it's very difficult. So you might type in filter here. You can grab it. And notice if I drop it in this line before I get the spectrum, it's going to first apply a filter and then we can calculate an FFT. And if I double click here, I want a band pass and I could actually make that 30,000 to 35,000 hertz. Make sense so far?
Yeah.
And we'll hit run here. And now I got some filtered data. So originally, when we looked at it, it was hard to tell the difference, right?
Correct.
But now, if we look at the data with the filter applied and without it applied, I'm starting to see a bit more red there. Would you agree with that?
Yep.
Now, filters, they have another property here, and that's the filter order. If I increase this number, what does the filter order do, Steph?
Changes the steepness of the cutoff.
So let's say I really want to really concentrate on that band. I could increase this filter order by a factor of 20, for example. That'll make a much sharper filter. And now let's see the difference. How about now? Is it even more pronounced, would you say?
Yeah, I think so.
It's hard to remember from a moment ago, but I think you're seeing a lot more red right now than we were a second ago. By applying this filter, we're able to see a much bigger difference than we were originally. And again, we're doing something kind of weird. We're taking advantage of a very high frequency that's out of the range of a normal accelerometer. The reason it's quote unquote out of the range is because there's a resonance in the accelerometer at higher frequencies, and we want to take advantage of that to be able to measure the difference between the good and the bad bearing, to measure this very faint impact vibration that's happening in all this data. It's mind-bending for people that are used to using accelerometers in the normal frequency range. Okay, so visually in the time domain, I can see a big difference, but I might have a bit of an issue here, Steph. If I bandpass filter, so I allow only frequencies between 30,000 and 35,000 to appear, what might be a concern?
Well, you're not going to see the 120 hertz frequency we're looking for.
Yeah, and there was a few frequencies there, like the inner race, the outer race. They were all below 200 hertz. Well, let's take a look at that. So I had the spectrum here. If I go and look at the spectrum of the good and the bad bearing, yes, the bad bearing shows a lot more vibration up here, but down here, there's nothing going on. We really lost some information here, and we'd like to get it back. Do you have a thought on how you might find our 120 hertz fault frequency again?
We could envelope the time signal.
That's a very good guess. I think you might have been reading ahead in the notes there, Steph. Yeah, an envelope is one of the keys. And an envelope is not just something you can use for bearing analysis. You can use it for doing things like modulation, measurements, and there's a lot of other things. If we look at this signal here, the green signal is the signal that we're interested in. The blue is the envelope of the green. It's a slow varying signal in proportion to the original signal, right? It doesn't have all these dynamics, and it follows the outline of the signal connecting the maximums. It's always a positive function, so it doesn't typically go below 0, but just follows the signal. You see that there?
Yep.
And because it's kind of hard to show on the actual bearing, I'm going to take a little digression and show how an envelope works on a series of impacts. So pretend these are the impacts from the bearing. And because I don't have all the other stuff going on in the bearing, we can see the impacts very clearly. But you can see the time between impacts. They're about 0.6 seconds apart. We would expect them to happen 1.6 times per second. All right, I'm going to, like I said, switch gears a little bit. I'm going to go to this impact here. So I have this impact event. I'm going to replace it in there. I'm going to grab the envelope too, because we're interested in seeing how that works. So we got the envelope function. I'll drop that in after the filter. Actually, in this case, I won't even use a filter on this data because we can see these impacts quite clearly. But what I'm interested in doing is I'll grab the original time history, do a spectrum of it, and then I'll do a spectrum of the envelope. You follow that logic there, Steph?
Yep.
I'm glad you do, because it's getting hard for me to keep track of. I got that envelope data in the input basket. I ran the process going to the active analysis here. So we got the original time history. I got the envelope. If I zoom in, you can see the envelopes following the signal. You can apply a filter to it so that, like in this case, the envelope will only have frequency content below 200 hertz. If I make this cutoff frequency higher, it'll follow closer and produce more frequency content. If I look at the spectral content of these two signals, I got a red signal here and a green signal here. And that is the FFT of the original impacts. They're all very high frequency events, 400 up to 2000 hertz. The FFT of the envelope is in green, and you can see it has lower frequency content. Do you see that, Steph?
Yeah.
Again, the envelope has lower frequency content than the original signal. And one of the things we're interested in is if I put up this double X cursor, I can see visually the impacts. So again, this was just some impacts. It's not from a real bearing here. And I can do a calculation here and I can say, give me the frequency at which these are occurring. And you can see it's 1.69 hertz or so. At the, well, it's not super consistent, whoever was making these hits, but a pretty low frequency event. And if we were to look again back at the spectrum, is there a 1.6 hertz component in the red, which is the FFT of the impacts?
No.
No. If I zoom in though, and I get pretty low in frequency here, and then I put on a cursor, this is the FFT of the envelope, and you can see that right around 1.6 hertz. There's some harmonics of it. The envelope actually has the frequency at which the impacts are occurring, right? Each impact event, and this is kind of a weird thing to get your mind around. Each impact event really is a high frequency event, right? It's a very brief impact, short in time, so it has broad frequency content. So it consists of a very broad range of frequencies, the individual impacts. But the rate at which they occur, again, every so often in time, that's very low, 1.6 times per second. And that gets reflected then in the FFT of the envelope. We can pick up the frequency at which the impacts are occurring. And guess what, Steph?
What, Pete?
In the bearing data, how often do the impacts occur for the faulted bearing?
They'll occur at the fault frequency.
Yes, 121 times per second. What should happen is if we were to run our bearing data through this analysis, so I would do the bandpass filter, do an envelope, do the spectrum, I would expect to see that I want to see 120 hertz or so. What do you think, Steph? Do you think I'll be able to see that?
I hope so.
Okay. I thought you could do a drum roll or something. This is an exciting moment, right? Hit run here. Go to the active analysis. And here we have the spectrum. And in this case, it's the spectrum of the, I'll even maybe just go up to 200 hertz or so. The spectrum of the data that's been filtered first, bandpass filtered. Then it was enveloped, and then we have the FFT of the envelope. And notice we have one with the fault and one without the fault. Earlier, when we did this FFT, we could hardly see a difference between them, right? At 120 hertz. But how about now? Can you see a difference between the faulted bearing and the good bearing?
Definitely see that the red one's worse.
Yeah. I just want to point out this envelope analysis in general can be very helpful to find out the rate at which some kind of event is occurring in the data, whether it's a modulation or an impact like this. Without the envelope, we would not get the frequency of the rate of the occurrence of the events. There's like two different frequencies going on. There's the frequency of the event itself, like the high frequency of the impact, but also the rate at which those impacts occur. You know what I mean by saying there's two different frequencies?
Yeah. Yep. Oh, that makes sense.
So that shows us the difference there. By the way, the envelope was developed by a gentleman, David Hilbert. So 1862 to 1943, worked at, I don't even know if I'll pronounce it right, the University of Göttingen, that's in Germany. Not only, Steph, was he pretty good mathematically, he was also known for his stylish hats. So you can see there.
The most important thing.
And again, just to try and drive home the point here, those impacts had the high frequency content, but after we did the envelope of the impacts, did the spectrum of it, then we could get the 1.6 hertz peak. When we did that with the actual faulted and non-faulted data, it was able to bring out and show us the difference at 120 hertz or so between the good and the bad bearing, which we could not see just by doing the straight up Fourier transform of the data, right? If we just took the data, did the FFT, there was hardly any difference here, right? These high frequency content impacts were creating a difference or indicative of the fault and indicative of a fault that was developing early, some sort of pitted thing on the outer race that was causing these small impacts. All right, I think that's everything I had to talk about there, Steph. Hopefully that made sense to everybody who attended.